Awesome. So I'm going to be presenting to you a method of trustless sale of encrypted information. I'm just going to go through the high level of the project before I dig into the code. So the aim of this project is really to provide a mechanism for the sale of encrypted data, something that's very hard to do like on classical chains like Ethereum and blockchains that are completely public. Um, and really, the problem is if someone wants to pay money to get access to a piece of data that only they can decrypt, and the entire process does not involve any third party and allows Bob to trust that for the payment that he has provided, he is going to be able to decrypt the correct piece of data with a high degree of integrity. So, and this problem gets even harder when you have one piece of data that is stored and encrypted and you want to give it to n different Bobs, which means you don't want to re-encrypt, or you don't want to continuously re-encrypt this piece of data with other people's public keys. You just want to encrypt it once and allow access control to that encrypted data in a trustless manner. And obviously, there's a lot of ways of doing this, but a lot of them leak the secret key if you do that all in public, which is not something you want. So the method that I approached implementing the solution for this is really to create a Merkle tree where the leaves of the Merkle tree are the ciphertext, i.e. the piece of data that Alice has encrypted, wants to sell to other people for payment in a trustless manner. And so she'll encrypt, C1, C2, CK to CN corresponding with the N leaves of the tree. And the method that she approaches this with is using SK, a symmetric key that she derives. And we actually commit the symmetric key to the public state so that when consistent changes or additions are made to this payload, we can verify that the correct secret key is being used, because in the prover, we can actually run a hash of it and check that that is in fact the correct secret key being used. Any questions till now? I hope this is all making sense. If it's not, this is a great time. I want to make this as interactive as possible. But if there's no more questions, basically the leaf add operations involve verifying that the secret key that was committed to in the initial setup is the key that's being used by just basically hashing the secret key and verifying that it is equal to the commitment that was posted, and then consistently encrypting it and using symmetric key encryption using the SK. Now, there's still a problem here. Where did the symmetric key come from, and how do we ensure that that symmetric key is given to other people, let's say Bob, so that they can decrypt it? Because we don't want to release the symmetric key to the public, but in an exchange over insecure mediums, how do we actually go about doing that? So I took a hybrid approach. What I do is I encrypt the secret key and post it to the public state as well. And we'll actually use public key cryptography here to re-encrypt that secret key, the symmetric key, sorry, that was used to encrypt the payload that Alice wants to provide to other individuals. So the secret key derivation is fairly simple. You take a random scalar and you just multiply it by the generator of the group. And that forms the symmetric key that we use within Poseidon to create the key stream that we do a combination with the plaintext with. The encryption step itself is done by basically taking a deterministic value that is derived from a salt and Alice's private key to determine another value, a group element. And this group element is added to the symmetric key to basically encrypt this key. Now, the unique thing about this is that we use a salt. So if it was ever the case that this value HG that you see above was ever leaked by mistake, Alice has the possibility of just changing the salt underlying it and still using her private key. So she doesn't have to lose her private key if she loses HD within this protocol. And we store that encrypted symmetric key onto the public data as well. And finally, when you want to rederive, basically re-encrypt the secret key, and this sort of embodies that access control mechanism of providing Bob access to that data. What will happen here is we will rederive the symmetric key that was used to encrypt the payload by Alice, by her passing in her private key. And then we use a Diffie-Hellman exchange to derive a common key between Bob and Alice using Bob's public key and Alice's private key. And by doing that, we present this shared key, and this shared key is common between Bob and Alice, and we then re-encrypt the decrypted symmetric key with this shared key, allowing Bob later to decrypt it, because obviously Bob can use Alice's public key and his private key along with a generator to rederive that shared key. And this sort of solves that problem of Bob can now pay money into a contract and get back the data without trust. One thing I noticed is that there's a statistical attack in the way I'm using Poseidon because of the fact that if there's a plaintext distribution and we have a ciphertext distribution, because I'm simply adding the key stream and I'm repeating the use of the key stream, over time it's possible to rederive the key stream. So what I did was I'm hypothesizing actually adding a initializing value to the sponge construction of the key stream to facilitate a little more entropy, so that every time we don't basically repeat using the same key to encrypt C1, C2 through CN, in terms of like each block would be one field. So we don't use the same key to keep encrypting that same field. Now, if that all didn't make sense, I'll dig into the actual code now so that it hopefully makes a little more sense. We can run through the test itself, which is basically going to also describe what's going on here. So here we have set plain text to a random value. It's a field value 23323. We deployed the contract here, and we initialized the Merkle tree locally. So now we know that the roots of these trees are the same locally and on the contract. And then we do the generation of the re-encryption key here. And we're getting Bob's rekey, which we're doing the Diffie-Hellman process here to rederive the original key. And the re-encryption key is passed to Bob. Once Bob has that re-encryption key, he then redoes the process to generate the key stream and subtract that key stream from the encrypted data, giving him back the plain text, which, as you can see, is 23323, which is also the original, or this is the decrypted value. This was the original plain text value. As you can see, they're equal, which means that decryption worked, and there was no element of trust between Alice and Bob. And Bob knows that the integrity of the data is true, and that they can now pay for that data because they did get the correct piece of data that they had paid for. So yeah, that's it in terms of the app itself. If anyone has any questions around details of the contract or just any questions in general, I can also